Hi, friends of the sun. Welcome to a weekly reading group happening every Monday. We just have some authors of cool papers join us here, and then we discuss their cool papers with them and they answer some questions and so on. This is all happening on Zoom. You can find the information to join the sessions yourself down in the description and yeah, just talk with the authors yourself. And today we're joined by Rob Brekelmans, and yeah, we're talking about some a twisted sequential Monte Carlo for sampling, let's say, sequential samplers. And yeah, I find it pretty interesting, the connections that are to all the twisted SMC literature, all the RL literature, the maybe also contrastive learning literature, and oh, also especially the diffusion model connections, which I hadn't thought about at all before when reading the paper itself, and only now in this discussion with Rob became apparent to me. So maybe you also find it interesting. Let's go.
I'm a PhD student at the University of Toronto working under Roger Gross. For this paper in particular, it's joint work with Rob and Ali as well. Anything else I should cover or?
Nope. Rob, what about you?
Okay.
Yeah, sounds good. I'm a postdoc at the Vector Institute, working with Ali and Roger. Yeah, and I did my PhD in Southern California. So, yeah, I guess we can get into our work on probabilistic inference in language models via twisted sequential Monte Carlo. So it's really just take what we know from MCMC and sequential Monte Carlo and apply it to language models and profit. So maybe I'll start by just kind of introducing the task of control generation in language models, and maybe like throughout and maybe in the discussion, we can kind of hint at how some of these concepts are going to be related to controlled diffusion processes, control generation in those in like continuous spaces and dynamics. Then we'll introduce twisted sequential Monte Carlo sampling, and we'll see what these twist functions are and how to learn them a bit later. So just to ground the setting, yeah, I'll be talking about language models, but like insert your favorite discrete sequence generation task, generally with an autoregressive model. So like, let's assume we have this pre-trained or prior model, P0, which generates responses based on a prompt S0, kind of this familiar chatbot setting. But we would like to, sample some interesting behavior from this language model based on some potential function phi, which modulates this base model. So for example, like a common setting is that we train like a reward model from human preference data, or like one response is preferred or not. And then we can, treat this potential function as e to the beta r, which corresponds to like wanting to sample high reward sequences. Yeah, so let's just treat this P0 times phi as an unnormalized density, which is going to define our target distribution or behavior we want to sample. And this will be easy to evaluate, but if we want to give a normalized distribution, this is difficult because we need to calculate this normalization constant, which sums over all possible sequences. And just to reduce clutter, we'll remove the dependence on the prompt. So we'll just write distributions over sequences of length up to big T. Okay, so a challenge in this case, so like this particular language modeling, is that like the target information, this potential phi, is given over full sequences only. But in practice, we have to generate tokens autoregressively, like, or we might want a way to evaluate the quality of partial sequences. So like some functions of S1 to 2.
But like, so here, this quality isn't really the full quality, so to say, but just this, like not the combination of high likelihood and meeting our target value or the reward function, but it's only capturing the reward function, right?
Right. But I guess the way we're going to use it, just to fast forward, is that like, okay, sure, this is like the next token generation distribution. That's fine. But like, we'd like to be able to sample from the marginal distribution over partial sequences, like given that they have high reward, for example. This will become more clear in a second, I hope.
Right.
Is that, yeah. So yeah, it's mostly capturing the reward. Yeah, cool. Yeah, so people often, this is exactly like the challenge of reinforcement learning. So that's a natural approach which people use often, like kind of this reinforcement learning from human feedback. But we give kind of a probabilistic perspective on all of this, which will kind of encompass soft RL style methods as special cases and maybe lead to some new perspectives. So in particular, we focus kind of on sampling methods, like ways of sampling from this target distribution. And just to preview, I guess I don't know if I'll talk about it too much, but there's we can just think of this as a kind of control generation problem in the language models, where we want to modulate, the reference distribution to generate high reward sequences. And a lot of the same ideas would come up if you were trying to like take a pre-trained diffusion model that, generates a diverse, all different classes of images, but we wanted to control the process such that we generate cats at the end, as at the noiseless sample, let's say. And so, yeah, like I guess forget that classifier free guidance exists. But yeah, now we can think about wanting to sample intermediate transitions, conditioned on the endpoint being a cat. And this will translate to like kind of a gradient term added to the diffusion score.
Okay, so why are you saying classifier free guidance?
Maybe this isn't what you would do in practice. Like just take the pre-trained diffusion model and then try to do learn some guidance term. But
okay, I see. So you mean you are talking about this is somewhat analogous to doing classifier guidance, right?
Yeah, exactly. Actually, yeah, it's good that I have it here. So like this psi term that we'll talk about a bunch later, but haven't properly introduced, in that case would be the probability that the endpoint, that the classifier outputs, cat based on the final token, based on the final image, but marginalized over future generations. So it's only conditioned on XT.
Yeah, like a noisy classifier. Okay.
Yep. Okay. And so like, maybe this is useful because like if discrete diffusion seemed to be the hot thing at ICML, but it doesn't seem like we're going to be able to just add, gradient terms to achieve guidance. So maybe some of these ideas will be useful. I'm just trying to like put this in the back of your mind if you're more working on diffusion than language models. Okay, so another step that I kind of want to make is to like replace, I want to talk about this as a posterior inference problem, and may need a little bit of notation to do it. So instead of just treating this as like an arbitrary potential function phi, I want to think of it as the likelihood of some observation random variable OT. And so in the previous case, it was just like the class that the output, that the classifier outputs. And we'll go through some examples. So yeah, a classifier is a natural example. So the target distribution is over full sequences conditioned on being classified to a certain class, such as like high sentiment responses or toxic responses if we were doing content moderation, something like this. If we're doing like red teaming of a model, we may want to condition on generating future tokens based on what we've generated. So like we might want to push the model to see if we can sample, like, here's how to do something bad. We might want different attributes of the full sequence, such as like that the sequence rhymes if you want to make poetry or something. Or this RLHF case, just like some arbitrary modulation function, also fits into this framework, even though it's like not necessarily obvious what the observation variable is. But you can think of the observation variable as being like the output of rejection sampling, whether we accept or reject a sample. And then on average, we'll obtain a sample from this distribution that we care about. That's not so important, but it's kind of a footnote in the paper.
So let's go.
But I mean, I think this is like pretty flexible way to, this isn't like a restriction that it's like an observation random variable. Like we can kind of plug in any arbitrary importance ratio in here and it won't change, at least the formulation.
So you'll have the p twiddle. No, well, why do you have a p and a p twiddle? What's the difference?
Yeah, good point. Sorry about that. So so the tildes are going to be unnormalized densities. So this is normalized, so that's the Z. And I think we'll write all of this as like PS1 to T given OT as kind of an unnormalized density. And then we don't necessarily need this to be normalized because it will be absorbed into the normalization constant and give the same posterior. That's like a minor point, but tildes are unnormalized. That's a good point. Good thing to emphasize. Okay, so the way that people usually go about this or the perspective in kind of RLHF is that they treat this target distribution or kind of justify it as the solution to this optimization problem, which is we want to maximize the expected reward subject to a KL penalty to the prior distribution. And often will, kind of fine tuning amounts to optimizing this using policy gradient methods to optimize Q. So this is like PPO, or you could use reinforced gradients. But instead, like kind of the perspective that we're going to take is that we're going to, or actually, I mean, if you look at this objective, you can think about it as like the evidence lower bound from variational inference. So it's a bound on the log normalization constant. The gap is equal to a KL divergence between Q and the target posterior P. And, at the end of the day, we'll want to take samples from this Q as approximate samples from the target distribution. And, these will be kind of as good as Q is able to match P. So maybe that's just like kind of some of the probabilistic language that we want to bring into this problem. So we're going to focus on just like ways of sampling from the target distribution, rather than just like restricting ourselves to this particular optimization. And as we mentioned that like a closely related problem is going to be how to estimate the log normalization constant. And so as we kind of argue in the paper, various sampling schemes of which we're going to describe a few now. They're all going to lead to bounds on the log normalization constant. And the tightness of these bounds indicates sample quality, right? So previously we had an evidence lower bound, and its gap reflected how well our samples from Q matched the target distribution. Yeah.
So we're going to have this, like you're saying, the expected reward, which we can compute by like now sampling a lot from our model and evaluating its reward. That will be a lower bound on the yeah, it will be a lower bound on the thing that's in your box up there, right? And then somehow we can convert this into a bound on the normalization constant as well. Is that what's going on?
Yep, exactly. So
okay, so you're now just logging all the stuff, and then
sorry, so actually this is from, if you just rearrange this objective here.
It's not clear what the here was. There was no pointer.
Oh, sorry, this this objective. If you just pull the P and make this
the screen is not changing. Ah, yeah, now it's changing.
So take this here. Take this here.
Sorry, so this beta scales the R. And in the KL we have log Q over P. And so we hit this with the next. Okay, so writing it like this, and then we can do Jensen's inequality.
Mm-hmm.
And then this is Z.
Okay, and yeah, okay, so not just the expected reward, the expected tilted, or the expected likelihood tilted
Regulars.
by the reward.
Yeah.
Okay, then so why do I care about this? Like, why do I want to bound some normalization constant?
Yeah, so I mean, I guess it is like usually, I mean, I don't know, that's how like Bayesians do model selection, or if you want to evaluate likelihood of VAEs, marginal likelihood of VAEs or something. But like, I guess it's not like a crucial in itself. Like we described, like if you want to evaluate KL divergences between, Q and P, this target distribution, you need to estimate the log partition function. So to evaluate like how well we're doing in inference, I think is our argument as to why this log Z is important.
But this is not for the sake of quantifying, or this is for the sake of quantifying how far away we are from our target distribution, right? And not how far away
exactly.
we are, not for what this KL is that you have written down on this slide.
Oh no, usually we can just estimate this using sampling, or like during optimization for sure using sampling.
And so we can't say how far away, but yeah, this seems kind of meaningless to me. This target distribution is something that we tune anyways based on like some hyperparameter with the beta, and then depending on many different betas, you would get many different gaps in your current training setup. And yeah, so why would this be relevant?
Well, so for every different beta, you need to do a different optimization or a different estimation.
Yeah.
Essentially. I think this could give you insight into like if you looked at the curve of all the different betas for a fixed reward function for P0, this would kind of indirectly give you information about the moments of P0.
The moments of P0. Why is that not?
Yeah,
why-
it's like just a Taylor expansion of the log normalizer. Maybe that's not super
Interesting.
crucial. Yeah, but because this is like a cumulative generating function essentially. The
Yeah,
log of it.
okay, sure.
Can I offer like
yeah.
a stupid response to the question that was posed earlier?
Because Stephen was struggling with this exact question, so yeah.
Yeah, so I think to Hannes' earlier question, I guess, like why do you care about this posterior distribution that includes the beta? I think one simple stupid answer I'm going to give is that it's kind of what RLHF is doing. So people in practice do RLHF where you have a regularization based on beta. And so whatever beta you use for regularization is the same beta that appears in this posterior distribution over here. So if you care about doing RLHF for making your language models better, then you care about this posterior distribution that we have on this slide here.
Well, why is that? So does my RLHF procedure yeah, does it become better somehow if I can estimate the log partition
Oh,
function?
okay. No, good. So let's move on because like I guess we're gonna like sorry.
No, I mean, right, you have your procedure of doing a twisted SMC for sampling language models
yeah.
and so on. And yeah, sure, maybe this now works better and than RLHF or something like that. But and in the paper, I'm not sure if there are no evaluations of it, but it seems like there are no like DPO or RLHF comparisons, but the evaluations, they are all like focused on how well can we estimate this log partition function. And I don't get why we care about the log partition function still. And I don't
Yeah.
quite see how.
So what I think it will become more clear in like 1 second. Like, so I guess the shift is that like instead of like, just optimizing this, we're focusing on sampling from this distribution. So let's just like consider this problem.
Yeah.
Like almost for the rest of the talk. Like the paper is written more in terms of estimation. But like now we're gonna come up with like more complicated sampling schemes. And we're gonna preserve bounds on the log partition function. Okay, whatever, that's fine. But like we can tell if we're getting a better sampler if this lower bound is increasing.
But
and so I'll show you an
can
example of
tell
that right
we're
now.
getting a better sampler for this particular target distribution, but we don't even know why this particular target distribution would be the right one. But we can go with beta from 10 to the -5 to 10 to the 10 to the 5, and we have no idea which one of those is the right one, and this is like a hyperparameter that ranges wildly. So I don't see the relevance of telling how well we do for one particular beta, because we have no reason to believe that this particular beta is the right one.
I agree, but it's just like a hyperparameter from the RLHF problem. Like, production RLHF people like need to set a beta and then they optimize towards one beta. And so like, I think those are interesting questions, but like we're glossing over them. And we just pick a particular one and we want to try to sample.
Okay, then it seems to me less relevant in practice to estimate this log C, but then let's just talk about the sampling now and how you
So I think you would get something if you had like, but you would learn something if you did this across a number of different beta. I totally agree. Like that's an
Maybe
interesting. Yeah.
I'm not 100% sure that this is the right point to ask, but maybe one way that it can be helpful is to view this from the point of maximizing feature information. Because if I understand correctly, then it's kind of the same idea, right? Minimizing variance and maximizing feature information here. But we want essentially to have low variance of those predicted modeling targeted distributions. Or maybe it's a bit early to ask about this.
Is this something that you understand, Rob, or not?
Not precisely, but yeah,
Okay,
not
then
precisely, but
maybe I will
have a
ask
few-
later. Yeah.
Yeah, then Denise, let's skip this point. Let's skip this
ask
point
later.
and talk about it later. Yeah. Rob, let's do
I have a
this
bunch of papers from in my PhD. It was a bunch of papers on like what happens when you vary this beta and like relations to information geometry. So, but I don't. Let's table all of that. Okay, so let's just like to reset. Like I think this will become more clear that like we're going to take a sampling perspective for a particular control generation target distribution, and we're going to want to evaluate how well we're doing. So let's like take maybe the Q that we learned here, the approximate distribution, and a simple thing to do is just sample from it k times. So in this case, like full sequences. And then we said that we could evaluate this unnormalized target distribution. And so we can weight each of our samples based on these importance weights and like resample proportional to them. Sample a categorical with these kind of normalized weights and return the sequence in this index. So, here are the p tilde, or the reward is rewarding positive sentiment sequences. And I love this book, best book ever, is likely, is going to have a high weight. Okay, but now like this, if we wanted to ask like, what is the distribution of S1 to TW? Like, what's the distribution of the chosen sequence from here? It's not clear, like we don't know its density because we have to marginalize over all draws of K sequences and then the sampling procedure, the resampling. So this is like kind of hard to get a handle on, but we'd still like to like evaluate how well we're doing. So that's where we can calculate log partition function bounds. And these bounds are going to improve as we increase K. So if we have more samples to choose from, the one that we end up with will be better. And we get an exact sample from the target as K goes to infinity. So maybe like this is a little bit more context about like how we can use these bounds. We want to preserve bounds on the log Z. We can use them to compare, like, for example, sampling with different numbers of K. Okay, but like this is obviously going to depend crucially on how good, like, okay, K equals infinity, that's fine. But this procedure is going to depend crucially on how good this proposal is, Q, how closely it matches P. And, in theory, it's kind of shown that you're going to need samples proportional to the KL between P and Q. So, we'd kind of like to do something better than this. And that's going to be kind of the motivation of Twisted SMC.
Okay, so I think I kind of see that for maybe fine-tuning our language models, estimating this log Z, I don't know how maybe it's not so relevant, but there could probably be some other applications where we really are sure what is the target distribution that we need, and then it's good to know, we drew this many samples and now we sort of have a representative, now this is a sort of representative population for the distribution that we're targeting, right? This is something that we could then tell with with having the log Z.
Yeah, exactly, right? Like, I mean, you don't really know how to compare different unnormalized densities, this thing you can evaluate, but then if you have the normalizer, then you can kind of convert it into a normalized distribution. Maybe something else I'll say is that, like, in kind of variational inference, this is common where, like, this k-sample bound that I just described is like, you can also optimize this lower bound on the log Z. And that's usually like, it's a common principle for deriving optimization objectives. And so like the k-sample bound is tighter in general. So like that's often preferable in like the VAE days. So
yeah,
cool. Okay, so just like, I guess visually to get the intuition for like how we're going to improve things with Twisted SMC. So, previously we were just resampling after generating full sequences, but, if a sequence starts with "this book was bad," then we can, safely assume it's unlikely to have high likelihood under a positive sentiment classifier. So we'd like to be able to filter this out somehow. And the way that we might do this is by like obtaining some importance weights for partial sequences. This is the like kind of evaluation function that I mentioned at the beginning. Okay, but like, what's the right way to evaluate partial sequences? And it's really like using the marginal of the final target distribution is ideally what we would like, because then we can kind of sample proportional to the target distribution all the way along the sequence. So that's what I've mentioned here, right? We'd like to marginalize the full posterior over full sequences to a posterior over, sequences of length 2. But of course, this requires marginalization over all future tokens that start with this given prefix.
So instead, you just train a model that tells you how do you need to tilt your current probability to get this probability, or how do you need to scale your current probability to obtain the unnormalized version of this probability. Well, it is unnormalized.
Yep. There'll be notation in like one slide.
Yeah.
Right. Yeah. And so like we can always evaluate the base model, we assume. And so we just need to estimate the kind of modulation factor, or it's going to be a density ratio of its own. Okay, but if we had these, golden scoring functions, importance weights, intermediate marginals, what we could do is like, similarly to what we did at the last step of the k-sample case, we could just resample according to these importance weights. And, this book was bad, it's going to get a low score. And the unlikely to be cloned. So we sample with replacement. And, then we can keep generating from here. And this will give us better like final sequences, is the hope. Okay, but like we need to learn the good scoring functions for evaluating intermediate distributions. So as Hannes was saying, we're going to write down the target unnormalized density at an intermediate step. So this is going to be, some kind of posterior over the endpoint observation. And we can evaluate, we know the base model. And so we want to learn this factor, which, similar to the cat case, is going to be proportional to the probability of this observation given the partial sequence. Yeah, you can write it as like an expectation over future tokens as well. And so like this is, ideally what we would use to reweight these partial sequences. And it's intractable, so we need to learn a model to estimate it. And so, as we said, we're just going to try to learn this modulation factor, or this expected future probability of the observation. Okay, so
now you're
I think
going
I'll give
through the
kind of
through the sampling procedure once again.
yeah. So what do we do if we have these? So we have used these blue size to parameterize intermediate target distributions, and we can use these to construct importance weights. Yeah, so I guess it's mostly the same. We've seen this. Resample according to the weights. Hopefully filter out low red sequences. And sorry. Yeah, at the end, we'll also return one sequence. You can think about it like this. And then hopefully this one sequence will be better than what we had before, either sampling just from Q or sampling K times from Q and picking one. But if we've done a good job of filtering partial sequences, then we'll end up with a better sample. And this also preserves the property of being like a lower bound on the, okay, yeah, here we are. So this also, so hopefully leads to improved sampling and also gives us an unbiased estimator of the normalization constant, Z, which translates to a lower bound on log Z. And actually this holds like no matter what we did in the middle. Like you could, I mean, it won't necessarily be helpful if you just have bad intermediate scoring functions, twist functions. But as long as we resample the final step according to the target distribution, at least asymptotically, this K approaches infinity, then we'll kind of be okay. So that's like a weak guarantee, but allows us to keep making these same kind of statements about twisted SMC as we did for the previous cases.
Now I'm confused. Like, does this assume that our psi's are correct? The twist functions?
Right. No, they don't.
Okay.
So it's like
so
unbiased
no.
in an expectation. Yeah.
Okay, so it's fine that our twist functions are wrong, right?
Yeah.
Yeah. Okay.
As long as like at the final step we do the right reweighting, and certainly in the K approaches infinity case, that's all gonna even out. Like we'll find the right sample.
Makes sense. I mean, we say we have our final. Yeah, it might just be that our twist functions are super bad, and they actually make the estimate. No, never mind. All right, let's go.
I think you could do worse, but you could just reverse it, right? Like no, and if there's no intermediate resampling, then we fall back to the previous case. And so normally what people will do is, again, this like depends on the twist that you have, but do adaptive resampling like every couple of steps based on effective sample size. Yeah, Hans.
Well, in terms of words, like the SMC is just if we have a pool that we're like a pool of samples that we're like updating and resampling with every update, and the twisted then means like twisting is maybe the analogy of tilting, but for marginal distributions or something like that.
Yeah, so I'll just like go straight to this. Like I wasn't sure how to talk about it, but I mean, in like the twisting really comes into play because like to mirror the RLHF setting, we assumed that we had like no intermediate target information, right? There was like no sense of how we're doing in between given to us by the problem. But like in kind of a hidden Markov model or something like this, it may be natural to have like actual observations that are emitted at every time point, or at least some intermediate time points. And so we can use these to construct target distribution, intermediate target distributions in general. And so like, actually for like, there was a previous paper on SMC that was doing this kind of thing, like, you know, we'll only accept partial sequences if they don't contain curse words. So we can do resampling according to like some kind of hard-coded conditions. Or they even do like, you know, evaluate partial sequences with other LLMs, like prompted with my favorite teacher and my favorite ML researcher to try to get like, you know, if you have high likelihood under both those prompts, then maybe you're Andrei Karpathy or something, right? Like, so this is like a kind of design of the problem. Like if you have prior knowledge about your problem, you can kind of inject it to give intermediate target information. And then the twists are just estimating the future information, right? So like this may already be an interesting intermediate problem without any twists or twists equal 1. And I guess that's called like filtering SMC. But the twisting is when we want to try to estimate the future information.
Okay. And then do we like the twisting is if we want to estimate future information. And then is it if we want to estimate future information of a tilted distribution? Like,
Yeah.
I'm just wondering, like, where
That's
do
it.
people, like, why do people use the word twists? And then, like, we have tilting and twisting, and then maybe twisting is now the analogy of tilting, but yeah, for marginals, not for the joint. Yeah. Okay.
Yeah, it gets worse. Like they even call the like approximate is the twisting potentials, and then the optimal is the smoothing. So like
Yeah.
I don't know. I can't quite I can't tell the
see.
story of the
Okay,
game.
so we don't actually we don't want twist functions. We want smoothing functions, but we can only get
Yeah.
twist. Okay.
Nice. Yeah. Use it in a sentence. So you've learned the words, learned the lingo. Nice. Perfect. Okay. So yeah, how do we learn these things? And like in the end, I'm going to reveal that it's, you know, maybe the, you know, RL might be a good way to think about this after all. Or naturally, right? Like naturally it's going to have an analog in reinforcement learning because it's kind of solving the same problem. But maybe this probabilistic or sampling perspective gives us, you know, kind of other ways of estimating these intermediate marginals. So we propose learning twists using kind of matching each marginal using a KL divergence. I guess this is P, sorry. And so this is really just like energy-based modeling of each marginal. If you remember that each of these was P0 e to the log psi.
Yeah.
But kind of a problem here is that like, okay, yeah, energy-based modeling is usually hard because we can't sample from the induced energy model. But here we also don't have exact samples from the target distribution. So we have to do kind of two different important samplings, which you know, maybe isn't ideal, but you know, in the first term for like the kind of data term, we do importance sampling based on full sequences and the given reward function.
Okay, wait a second.
And then,
So
yeah.
we need to have data with the reward, right?
This would be an exact sample from P equals P0 e to the beta R over full sequences.
Yeah.
And then actually really truncating it to partial sequences. Like we want a sample from the intermediate, the smoothing distribution.
So then we would have to train, if we wanted to do some RLHF or something like that, we would first need, and we only have preference data, then we would first need to train a reward function on the preference data, right?
Yeah, so that's like kind of separate and maybe follow-up work is like we assume that we're already given this final reward function phi, like you've already done classifier, you've already learned a classifier on preference data.
Yeah.
And so like DPO would be learning directly from preferred and unpreferred sequences. And so I actually haven't found a way to like, learn the correct marginals through learn the correct twist functions through directly from preference data, or like, I guess, improve upon just standard DPO. But yeah, that's a question and it's kind of separate. Like we just assume that we're given the reward.
Seems like it should be possible, right?
I mean, certainly if you get the optimal policy, then like you're fine. Like you know everything about its intermediates, but I guess it's just coming up with like different objectives because here we're optimizing an objective at every time step, right? We're kind of matching each marginal separately.
Anyway, let's maybe continue. So we have on the one side, we have these samples from our data for which we have the reward. So we have the samples from the tilted distribution. Wait, so we really couldn't do any RLHF even here, right? Because in our RLHF, the training data that we have, that's also like the samples, they aren't from our tilted distribution.
Correct. Yeah. Like when we were writing that, when we were writing this objective, which is what we can think about everyone doing in RLHF, like this requires samples from your like learned policy. And so it never involves kind of the target distribution. So like that's it's kind of it's a difference between like optimizing.
What the hell's going on here then? You need samples from your target distribution for training a sampler of your target distribution, but you want your target distribution to be one that is like not previously sampled and just defined by tilting another distribution with a reward.
Mm-hmm. Yeah, we kind of have two different energy-based models which are difficult to sample.
Yeah.
And so I guess like, okay, so maybe we can like move on from this.
Training data is not available.
Correct. But if we have some we have some information about the true target distribution. So we want to push up actually, I guess we want to push up the likelihood on when weighting according to the thing that we are given, and push down on things that are based on our learned ones. So like hopefully it still gives us kind of directionally an interesting gradient, but we're doing neither of them exactly. And I think that, yeah, that's definitely a downside of this. We kind of wanted to optimize the KL in this direction because like these twist functions, I think we want them to be mass covering, like not just zoom into one mode that you're always going to sample. You're always going to like reweight and pick that mode. So we'd like to learn using mask covering divergence. But yeah.
Okay, yeah, I get. Yeah, thanks.
Yeah, sorry. I think Rob said a lot of things and covered a lot of stuff in his response. So maybe if I can just pick out, and maybe this will help, is I think you raised an interesting point, which is something that we've also discussed, which is like, okay, you need samples from your posterior in order to do this gradient. But then if you had samples from your posterior, you don't need to solve this problem because that's what we're trying to do in the first place, right? So what's the point of doing this? And so what I would say is this formulation that you have on the slide here is kind of the ideal, right? So it's like, let's say, ideally, if you had those samples, then this is a thing that you could do. And then if you do this to infinity, then you get the optimal distributions as your twist functions and everything works out fantastically. Now, obviously, in practice, we don't actually have samples from the posterior, but the idea is maybe you can approximate those samples from the posterior, for example, using importance sampling or SMC or whatever have you. And as Rob was saying, because there is some true target information embedded in your approximation, the hope is that this gives you some useful gradient signal such that you're still learning something from this process, even though you only have approximate samples instead of true samples from your target distribution.
Okay, then so to estimate this expectation, you do not actually use samples from the target distribution. You use samples from the untilted distribution and you reweight them with importance weights for the tilted, toward the tilted. Okay, I see.
Yeah,
That
sorry.
makes sense.
Sorry, I failed if I didn't convey that. So thank you. I guess in some cases, like let's say we wanted to, so maybe like in the classification case, maybe we like sample a sequence. Like there may be cases where we have exact samples, like via amortization. So like, let's say we sampled the sequence and then sampled a label. Then we could use these as exact samples and kind of just learn the twist function for that label, that conditioning. And so that would not be good for rare classes that we rarely sample, but you know, there's some cases where we might have exact samples.
Yup.
Anyways, so let's get on to things that are less controversial. I think like that's probably, yeah, not this. Yeah, I mean,
Okay,
that one has clear issues that we mentioned. Yeah.
Now we know everything that's going on, right? We know how you do your twisted SMC to sample the for sampling, and we know how you do your training. You do your training by computing the can you go to your training slide again? No, your expectation. You estimate your expectation using samples from the untilted distribution and importance weight them to estimate the expectation of them in the tilted distribution. So you kind of have an unstable training target with that because you're in, like it has some higher variance through these importance weights and based on the sample size or the number of samples that you have there. But yeah, maybe you can use many more there. No, that's not the case. Yeah, and then this is happening on the one side, and then on the other side, you draw samples from your with your twisted SMC methods, and these then also go like you do a stub gradient. You put them into your phi t, and then that is the right side of this term.
Yep, exactly.
Okay.
Reweight based on that.
So, and there is the stub gradient that I talked about as well, right? Is there or not?
Yeah.
Okay.
Yeah.
Gucci. Thank you. Then this is all clear to me at least. Yeah.
Okay, so yeah, there are, and I think this like maybe slightly changes an existing method for twisted SMC, but this is kind of the like, let's treat this as a density ratio estimation problem or like learning a probability distribution rather than what we'll talk about now, which is just kind of like RL, or what we'll talk about now is just learning the twist functions directly. So I guess my animation is a little off, but if we remember the, kind of how we were parameterizing the smoothing distribution and our approximate twisting distribution, kind of the optimal twists measure the expected future likelihood of the observation. And so, one way to learn this is to just directly do regression. So if we just optimize the squared error loss in expectation over future tokens from P0, then the conditional mean is going to be the minimizer, and we get back what we wanted. So this amounts to, actually, I mean, you can sample any S1 to T, small t, any way you like. Sample future tokens under the reference model and regress against the observed likelihood. So, for every, I guess, I think we reuse samples in practice, right? So if we do one rollout here, then like every S1 to 2, S1 to 3, S1 to 4 is going to regress against the final observation likelihood. Okay, so this is what it looks like in the RLHF case. And I think some methods end up regressing against, like doing this regression in log space, but I would argue that this changes the optimum and the role of psi. So
I mean, sorry, Rob.
maybe
Like, what's
yeah.
going on here? You're just introducing a different training method that has some addition, like, and we're then trying out both of these.
Oh, yeah, sorry. Yeah. So yeah, that was just
Okay.
one that like we came up with, and there's a lot of others across both the language modeling literature, the RL literature, and like maybe even fine-tuning of diffusion models.
And
So
why do we care about the others, or is yours somehow better, or like why are we talking about the others now?
yeah, so I definitely want to get to like, okay, so we had bold numbers on 2 out of 3 experiments in our paper with this contrastive twist learning method.
Okay, and the other
But
stuff doesn't work as well, or what?
so I think there's, like, we already highlighted a potential issue with our like needing to do important sampling in both terms. And I don't know that we like fully optimize the reinforcement learning. But I did want to, yeah, I don't know that we have like there's one way to do this at scale answer for you in the paper. So I think it's useful to have a sense of
I see.
the various different methods, and then like some of these different principles are applied in like diffusion, for example.
Okay. Can we maybe go with like the main I think now, so you already talked about the 6.0 or and now you're talking about the FUDGE?
Yeah, I didn't talk about 6.0 much, but
okay, so
yeah,
we're
let's
skipping
just
6.0 and we're
FUDGE.
only talking about the FUDGE.
Yep, and FUDGE is just regressing against the final observation likelihood.
the final observation likelihood, which is here the red part.
The red part, yeah. So like, you know, just from the optimality conditions, we know that like the thing we want to approximate is an expectation of the future likelihood just via kind of marginalization.
Okay, so we sort of optimize it with something wrong, or like no, not optimize it with, like we optimize, or we take the minus or the loss, yeah, the minus, the difference to something that we actually do not want the phi to be, but because we average over all future, or we take the expectation over all the future trajectories, this turns out to then become the yeah, what you write down below. This is the minimizer. Yeah, it makes a lot of sense.
Yep. Exactly. And I mean, it's the same math as in diffusion with the conditional score versus learning
Yeah.
marginal.
Right, lol. Okay. Right, you have your arrow points into the wrong direction, but because you take the arrow or your score over multiple, like, yeah, all the training examples, in expectation, it will end up pointing in the right direction. Yeah.
Yep.
Mm-hmm. Oh, no,
Okay, but yeah.
so even
more.
more losses, or
Yeah, let's
even
just like I don't know how we are for time, but
I mean, we
is
don't
there-
have a time limit. We have an attention limit.
I don't, yeah. Okay. Yeah, sounds good. I think the connection with soft Q learning or RL is important. So I suggest maybe I should have put that a bit earlier. Okay, so I'm just going to repeat this same optimality condition for these twist functions. And in the RL case, we want to, you know, this final likelihood is given by a e to the reward function. So if we take the log of both sides and scale it, we can recognize this as the soft value function in regularized reinforcement learning. So it's just a log mean exp over future observed reward. And you know, from this, if all of our twists satisfy this like kind of endpoint optimality, then they'll also satisfy a one-step optimality with respect to each other. And this is kind of just the standard Q equals R plus V in reinforcement learning. So another way to learn these twist functions is to do just kind of Q learning with RL.
Yeah, now you're just writing everything in the like in the energy space or in the reward space instead of
Exactly. Yep.
Okay. But then is this actually different from FUDGE? No, isn't this here just FUDGE?
Right. Good point. So this is FUDGE was based on this identity, always regressing to the end. And this is based on one step ahead. So,
Okay.
you know, this is the same. I guess it's in log space now. But now we're regressing against stop gradient of like what's implied by the next token by like our current, you know, this is a learned based on learned functions, but yeah.
This is almost like in one, like, is it fair to say that one is off policy and the other is on policies or something like that? Like in the one, I look at rollouts and then I look at my little arrow of the rollout. So in the bottom one, it's a soft Q learning, and in the other, I look at the arrow to the targets, but I take the expectation over all possible targets.
Yeah, exactly. So this is just like, I mean, but this is just a one-step one, right? And this one's actually kind of off policy. Like only this one step needs to be on policy rather than like big T minus small t. It's just one step. And so like you can do this under any sampling distribution that you want. You can do it off policy.
You still need to roll out. Yeah, you still need to roll out your whole inference, right?
Yeah, you do this at each step, and like each step depends on the next step, and so you get a loss at every step.
Okay. This is yeah, indeed kind of interesting. Yeah. Then let's continue.
Okay, yeah. So like maybe this is for RL, like maybe a slight shift in perspective. Like we in policy gradient methods, you kind of focus on learning this policy Q, based on that expected reward objective that we started with. And they also learn these values, V, or the twist psi, but it kind of only serves to reweight training gradients. But for our purposes, like I haven't even talked about learning Q yet, only on learning the values V or psi. But our focus is more on the values, I guess, because if we have good values, then we can kind of correct for any proposal Q using the resampling operations. So this might just like give you a different place to focus in standard RLHF if you're using this twisted SMC. But I should say, like, we would like probably to learn twists psi and proposals Q, which are kind of matched to each other. Like learn them jointly. So far I've only talked about learning the twists. And I'll just mention that like path consistency learning is a way to do this. Kind of a joint optimization. It's based on the KKT conditions of soft RL. It's used in GFlow nets. But one way you can think about it is just like minimizing the square of the log importance weights from an importance sampling perspective. So yeah, I just kind of mentioned that as a like joint optimization possibility. And then the final thing is just SMC for diffusion models, how it's been applied there. So yeah, I'm kind of done with our paper. But okay. Just to maybe, yeah.
Then what do you think is the, do you have any experiments or evidence that this is better for some sampling tasks?
Yeah, so I talked about briefly like that, we were just mostly talking about learning these twist functions without talking about the proposal Q. But it turns out like we can, since it's easy to normalize language models over the next token distribution, because like it's just right there in the forward pass of the transformer. We can take our twist functions and use them to sample next tokens. So like they were kind of framed as learning marginals, but they also like tell us how to sample next tokens. And so we evaluated those policies to approximate the target, P0 e to the beta R, against like PPO, which is what people often use, DPG, which is another policy gradient algorithm. So these are just like, optimizing one objective at the end over full sequences. And then also these twisted methods. So RLHF and FUDGE that we briefly mentioned.
Yeah, okay. So
So,
all
yeah.
these different ways of training your model, right? Contrastive RL60 FUDGE, and you evaluate, like you compare them all with each other based on this, based on this, on the gap, and then, that's the deal. And do you have some, or do you have a claim that this SMC or this twist learning is now something that I should do if I want to actually or if I want to sample my tilted distribution instead of doing some other scheme?
Right. So, I mean, in this like PPO, like maybe you have some twist functions laying around, like you've learned value functions alongside it. So one thing you could just do is like take your policy and reweight it by your value functions and see if it improves sampling. So that's like one minor tweak. So like, I mean, I guess that assumed that you already have these twist functions, but how you sample and at least the proposal are a little bit orthogonal.
Yeah, okay.
And like I said, like maybe you would, if you had this kind of inference time sampling in mind, you might allocate capacity differently during training. And so, yeah, I mean, I guess like what people often do is just like sample full sequences and take the best out of N based on the evaluated reward. And so this is, kind of our methods are focused on sampling from this particular target distribution. So it gives you some guarantees. So there's a sense in which it's the right thing to do, but I'm stopping short of making any always do this in practice claims.
Okay.
And especially for like hard problems where you have more idea of what you want to happen in intermediate stages. Just like sequential Monte Carlo methods in general are very useful. So.
Good.
Yeah.
And any other things you want to point out or that you think are pressing and that are important? Or are we close to an end and should go to some last questions?
Well, yeah, I think I'll just throw one more like related work on the table, but I guess any last questions would probably.
So in the contrastive learning objective, did you work on the info NCE part, or did you extend something else?
This doesn't really have anything to do with info NCE, I think. Like this, just one contrastive loss, and so basically, why do we call it contrastive? Maybe.
Yeah, that's a good question. Yeah, it's a bit of a stretch. It's not quite info NCE. Right, like I think the 6.0 is actually an NCE method, a noise contrastive method, like where we're trying to classify this posterior given the observation versus the prior. So this would be an info NCE objective with k equals 2. essentially, where you have a positive sample from the target distribution and a negative sample from the prior.
Yeah, maybe we can call it, we're contrasting your correctly, or your samples that are reweighted to be positive samples, and your samples that are come from your model, which are the negative samples, and now we're contrasting them by calculating their likelihood, or the marginal likelihood,
or the gradients. Yeah, I would think it was more like a contrastive gradient rather than like contrastive on its own means
whatever.
something else.
Yeah,
Yeah.
probably not.
Plus, you also refer to here the estimation via EBMs. So, what's that here?
Do you mean what is an energy-based model, or do you mean what's the connection? Like why?
Yeah. What's the connection between the noise contrastive estimation of EBMs here? Like the classification of P function verb versus the P not. Yeah. This the box here at the bottom.
Yeah. Just the extent that this pi. Oh, sorry. Just the extent to this pi has the form of like P0 e to the energy.
Oh, okay.
Where I guess energy is log psi here.
Uh-huh.
That's like why psi plays a role similar to an energy function.
Okay.
And if you just took the energy based maximum like then this is exactly like gradient of energy under the true and the approximate distributions.
Yeah, that's cool. Cool. Thanks.
Yeah.
Good. Then maybe do you want to say like one last thing about this slide? So there's
so
Brian
this is cool. Maybe maybe you are. Well, Brian maybe was, I don't know, overlap with some of you and was doing protein stuff. So I figured I'd mention this. Kind of twisted SMC for diffusion models. And so the I guess like I gave the cat classification example, but this twist that we've been interested in is written here. So it's an expectation over like future evolution of the diffusion. But then we classify x0. And so I guess what they do in this paper is they just estimate this expectation using a single sample at the denoising estimate, right? So we're already like trying to predict the posterior mean of y given xt, or sorry, of x0 given xt. And so we just kind of estimate this expectation with a single sample by evaluating the classifier at the predicted x0. And so like everything I was saying about all these methods about like the regression or the contrastive twist learning or soft Q learning were difficult because we had these expectations. But in diffusion models, we kind of have a ready-made approximation, which is just the denoising mean. So maybe I won't get into too many details, but it's a really nice paper. So then they can like use this to use these classifiers evaluated at the denoising estimates to construct proposal distributions, like using some guidance of the score function, and then also do resampling based on the classifier. So it's a bona fide twisted SMC method for diffusion. So
nice. Yeah, then more SMC, MC perspectives.
And then there's a lot more out there. So I just leave that up, and then that's really all I
Good.
had. So yeah, I mean, we just took sequential Monte Carlo, applied it to reinforcement learning from human feedback or control generation in language models. But a lot of the same, Twisted SMC. SMC is a well-established thing with a lot of connections with like optimal control. So yeah, there's a lot of cool literature out there.
What is this top right one? Discrete derivative free
Yeah.
guidance.
Yeah, that's kind of cool, and like applies to the discrete diffusion case. They essentially use this method for estimating twist functions.
Can you go back to the title? In continuous
Yeah.
and discrete diffusion and this diffusion. 15th of August. Okay.
Yeah,
I'll
I think
have a
it's
look.
super relevant. Yeah. I think their objective, their learning objective, I'm not sure that it has the right optimum for what they're using it for, but they do use that posterior mean, the denoising mean approximation, like I described. So
Okay.
I think that's a pretty useful trick.
Cool. I will. This seems to me a candidate for a future reading group paper. I
Next
will
reading
have a
group.
read.